So torque is a vector, and torque is represented by magnitude and direction. The magnitude is not hard to understand. It's just the measure of force's tendency to cause rotation. The bigger the magnitude, the bigger the tendency to cause rotation. The direction is a little tricky, and let's go through that in this video. So, direction of torque. Now, torque, in a physics perspective, math perspective, it's the cross product of force and moment arm. And when we do a cross product, we actually end up with an interesting direction associated with the vector. I'm actually going to present the direction of the torque a little differently and talk about the direction being an indication of which way a force will tend to cause rotation if that force was the only force causing rotation. So let's talk about that. So let me draw a lever system out like this. We're going to use the counterclockwise rotation is positive reference frame, and I'm going to put a force on here, right here. That force is going to cause tend to cause rotation about this axis of rotation. And now, to calculate the magnitude of the torque, we would use this equation, T equals FD perpendicular. We already know the moment arm, that's the straight line distance between the line of application of the force and axis rotation, the shortest distance between those two. I'm not going to talk about that here, there's another video on that. To identify the direction of the torque, we need to know this reference frame, and then we need to know which way this lever would tend to rotate if this were the only force acting on the object. So let's look at that. How do we determine that? Easiest way that I found to do that is to start at the tip of the arrow and then rotate or draw a line or a circle around this axis of rotation, ultimately to the tail of the force vector, but you cannot cross the lever arm. So I have to start here, and I have to go around the axis of rotation, and I have to come back to the tail of the original force vector. And we look at the direction of this rotation. That's going to tell us whether or not the torque is positive or negative. In this case, this direction is going counterclockwise. All right, counterclockwise is positive, therefore this force, if I put a number here, if I do 1 and 1, this torque would be positive. Why? Because if this were the only force acting on this lever about this axis of rotation, it would tend to rotate the object in this direction, counterclockwise direction, and our reference frame is counterclockwise is positive, therefore that's a positive torque. All right, let's do another one. I'll draw the same lever here, and I'll do an arrow here, and I'll do F2 just so that we don't get it confused with the first example. I need to start at the tip of the force vector. I need to go around the axis of rotation, and I cannot cross this lever arm, so I can't go this way. Okay, I have to start here, and I have to go around the axis of rotation to the tail of the force vector. That's the direction of rotation this force is going to tend to cause. In that case, that rotation is clockwise. All right, that's clockwise. So if that's clockwise, and given our reference frame is counterclockwise is positive, that means a counterclockwise rotation will be negative. So T2, F2, D perpendicular to T2 is a negative torque. The direction of the torque is simply telling us the tendency of the force to cause rotation in either the clockwise or the counterclockwise direction. Okay, that's all it is. So we can do a few practice ones. And now this time, instead of drawing only one force on the lever, I'll draw two, so we can see how we do each one of these. I'll draw F1 here, and I'll draw F2 here. Remembering our counterclockwise reference frame is going to be positive. So now what we do, we want to identify the torques about this axis of rotation. We have two forces, so we have two torques. So we have T1 equals F1 times D perpendicular 1. And now we need to assign the direction to this torque. Torque 1 direction. To identify that, we're going to start at the tip of the force vector, go around this axis of rotation, and you cannot cross the lever. So I cannot go in this direction. I have to go around like that, end up at the tail of that force vector, and I'm left with a rotation that's going to go in this direction, that's clockwise, and clockwise is going to be a negative torque. Okay, now let's look at F2. So we did that direction for this torque based only on this force acting on the axis of rotation. I did not concern myself with this force. We don't know which way this object is going to rotate yet. We don't know that. All we know at this stage to determine this torque, we need to identify, we only need to concern ourselves with this force and which way that would cause rotation if that were the only force acting on the object. So now we'll do the same thing here. If F2 were the only force acting on the object, I got to determine the tendency to cause rotation, what direction that would happen. All right, I start at the tip of the force vector. I have to go around the axis of rotation. I'll go around my original, and I'll draw something like that. Not a great circle, but close enough. If this were the only force acting on this lever, I'd rotate the lever in this direction, which is counterclockwise, which is going to be a positive torque given this reference frame. So T2 is F2 D perpendicular to. T2 direction is positive. Okay, so now I have two torques, one that's negative and one that's positive. And in our angular kinetic analysis, we'll add those two torques up and we'll understand the product of moment of inertia and angular acceleration. All right, but from this video, I want to make sure that you have an understanding of how to assign the direction to a torque. Okay, thank you.